Welcome to the last lecture of the winter school. I don't know what about you, but by now I'm pretty tired. So maybe you are pretty tired as well. So I'm maybe going to keep it a little bit, a little bit shorter or simpler. We'll see. I also realized that my first slides were always very boring, so I decided to put a picture. So this is one of the things that we're going to look at today. So, as you know, the last lecture will be about applications of arrangements. And in particular, what I'm going to talk about is how you can use these bounds on, well, actually here it will always be some kind of upper envelope or lower envelope to bound the complexity of something else that seems to be, at first, maybe completely unrelated to arrangements. But let's first briefly recall what we did yesterday. So we looked at, you know what an arrangement is. What we'll be mainly using today are these bounds on the upper envelope, and upper envelope in 2 dimensions. So if you have curves that are infinite, okay, and they intersect at most s times, then this is the complexity of the envelope. And if they are bounded, so segments or something like that, then you get this lambda s plus 2. Okay, and remember that all these bounds are basically linear, right? Linear times some very slowly growing function, alpha n or 2 to the alpha n or something. Okay, and we also looked at, single cells, and actually I forgot to put the K level, so I hope you also remember the K level, or maybe especially the technique, this Clarkson-Short technique, which I think is very nice, and you can apply in many cases. Okay, applications. So the first application I want to talk about is developing a data structure for ray shooting in a polyhedral terrain. Okay, so what's a terrain? I hope you all know that. Well, it's a terrain. Let's say the mountains near Tehran. And if you want to model this, have a 3D model, what you can do, or what there are essentially 2 models. One is that you say, okay, I have a grid, okay, which x and y coordinate, and for every grid cell you know the elevation. So this is called a grid terrain or a DEM, and this is what people often use in practice in geographic information systems. The other model, which is what we're going to use, which is sometimes also used in geographic information systems, and which is the most popular model in computational geometry, is that you don't have a grid, but you have a triangulation. Okay, and the disadvantage of having a grid is, well, let's say, what is this? Where? You wanted to avoid me from, prevent me from getting rid of this. Okay, so if you have a terrain, let's say this is a top view of your terrain. So let's say here you have some mountains, and here it's very flat. Then for a grid terrain, you would simply have a grid. And for all these grid cells here, the elevation is maybe the same, because it's simply a flat area. So that's a little bit waste of space. So in a triangulation, you would say, okay, maybe you have, I don't know, triangles like this, and then you need only one triangle. You can use one triangle to cover a big area. So that's why these triangulations are interesting. So what you do is you have the domain of your terrain, okay, so the XY area where the terrain is defined, and for every vertex you know what the elevation is. Okay, and then you get this terrain. So it's a surface in 3-dimensional space consisting of triangles. continuous surface defined maybe over some rectangle. And what we want to do is we want to do ray shooting in such a terrain. Okay, so I want to construct a data structure on these triangles such that, well, if I give you a point and a ray starting at that point, you can quickly find which triangle you hit. Okay, in other words, you say, okay, I'm standing here, I'm looking in this direction, what do I see? And just, well, a single ray. Okay, well, this problem has been studied by a number of people and a number of different variants. So you can say, well, my ray can start everywhere. Okay, it could start here, here, here. Direction can be anything. Or you can say, well, where the ray starts is always the same. But now you can have, I can shoot in this direction, or in this direction, or in this direction, or in this direction. Okay, and of course, well, this is going to be easier. So let me talk about this problem. Okay, so the first solution you could come up with is to say, since this point is now fixed, okay, I simply say, if I'm standing here at this point, and now I simply look at the whole terrain. So I'm not looking on one ray, but I simply take the whole view. So from here, it would maybe look like this. Okay, so you essentially project everything onto a viewing plane with this point as the center of the projection. And then you simply have, well, you partition it into places where you see this triangle, and so on. Okay? Now, if I want to answer a ray shooting query, what does it mean? Okay, well, here I'm standing. I have my view. Now I'm looking in this direction. So that means that I simply have a point here, basically where the ray intersects the viewing plane. And if I look at, well, let's say the cell in this arrangement of line segments or triangles, then if I do point location here, I know which triangle I hit. So this is very easy, but the disadvantage is that, as you can see in this picture, the amount of storage can be n squared. Okay, it depends on, of course, on the terrain. It depends on where this point Q actually is. Right? If this point Q would be, let's say in this particular case, above the terrain, so we're really looking from above instead of from the front, then, well, you just maybe see the triangulation. And so then it would have linear size. But if you have bad luck, it could have n squared size. So we want to get a solution which is uses less storage than this. Okay, so the crucial observation is the following. So suppose I again project everything onto the viewing plane. Okay? But now, instead of storing this whole complicated subdivision here, which could have complexity n squared, I only store the upper rim, as it's sometimes called. Okay? Using this, I can answer the question, do I hit any of the triangles, or do I pass above all of them? Right? Because now I just have to say, well, let's say the red one hits here, that means here, which is below this silhouette. And the blue one maybe goes above everything, in between these two, so that's somewhere here. Okay? So, and I can simply answer that question by doing a binary search maybe on this thing, and then find out, okay, this point is somewhere between this and this with respect to x coordinate. I check whether it's below. If I do a query with this ray, do binary search, I find it between these two x-coordinates, and it happens to be above. So how much storage do I need? Roughly linear, but how much exactly? It's already here. Good. You're cheating. Yeah, right, because this is basically an upper envelope of my segments. Right, so the complexity of this envelope is, well, we've seen that. It's an upper envelope of segments, n alpha n. So with only roughly linear storage, I can answer this question, right? Not which triangle I hit, but I can answer the question, do I hit any of my triangles? Or do I pass completely above all of them? So now the idea is to use this and, well, to also find out which one I hit. Okay, so maybe if you think about it, you already have some idea perhaps. So the idea is more or less to do some kind of binary search, you could say. So look at this picture. So this is a top view of my terrain. Okay? Here is my fixed point Q. Now what I can do is I do what I did before with this upper rim, but I only do it for the left part of the terrain. Okay? So now I can answer the question, does my ray hit any of these green triangles or not? Okay? If you hit any of the green triangles, then, well, I still don't know which triangle I hit, but I definitely know that the first thing I hit is not one of the white ones, because the white ones are behind the green ones. Okay? On the other hand, if I miss all of the green triangles, well, then either I hit all the triangles, or if I hit something, it must be one of the white ones, because I'm missing all the green ones. Okay, so now perhaps you can do some kind of binary search to find out which triangle you hit. So this is the idea, and now we have to make this more precise. So what I need is, I wanted to do, well, this binary search, and what? So let me go here. So here I say, well, the left half and the right half, but I guess, it's kind of not really clear what is left and what is right. Can you always split it into half and so on? So essentially, if we're going to do a binary search, right, we want to end up with one triangle. Okay? Because that's then in the end the triangle that we're going to hit. So what I need to order my triangles where the ordering is, let's say, consistent with the order in which the ray could hit them. So that's what I have on this next slide. So I want to order my triangles, T1 to Tn, such that if you have a ray, like, do I have a longer pointer? Like this one, okay? Then possibly this would, maybe it goes through this triangle before it goes through that one in the projection. So then also in the ordering, I want that one triangle to come before the other one. Okay, so I want to order it such that if you have a ray where in the projection you first intersect Ti and then Tj, then I should also be smaller than j. Okay, and then if I have such an ordering, I'm going to construct a tree based on this ordering. So this is my tree. Okay. In the leaves, I have all my triangles. where the ordering from left to right corresponds to this ordering here. Okay. And now I want to walk down in this tree to answer my ray shooting query. Okay, so how am I going to do that? Well, at each node, so this is going to be a 2-level tree. At each node, I have an associated data structure which can answer this test. Do you pass above all the triangles or not? Okay? So now when I start at the root, so probably I have the query algorithm on the next slide. No. It's probably later, so I may repeat it, but we'll see. So if I start at the root, okay, I look at this associated structure. I test, does my ray pass above this envelope or not? Okay? If it passes above, where do I go? I go to the right. So if it passes above, then all these triangles you're going to miss. So then I can go here. If it passes below, I know since all of these are behind these guys, I know that my answer is going to be here and I go here. And then I simply walk down and that's it. Okay? Maybe just a small question. Suppose you don't hit anything at all. Where does the search end? Yeah, so then you always go to the right. And then you end up with a triangle here. And then you check, do I hit this triangle? And the answer is no. And you say, okay, you didn't hit anything. Otherwise, you always end up at the triangle that you hit.
Sorry. According to the ring you made, I mean the red line, the red polygon out there, yeah. According to this parameter, we choose the left or the right of the tree, and we separate the search space. So in next step, in the level, for example, level I plus 1, we have to find another ring, or we should, I don't know.
Yeah, so with this node, I store this silhouette, this upper envelope of all the triangles that are here. But then with this node, I have another structure which stores the rim, but only for these triangles. Okay, so that would be, I don't know, some of these triangles here.
So we layer I think we found some cases to cut the search space. The layers of the search space that defines which one should be searched. And in each step we should spend n alpha n for finding these upper bounds, yeah?
And okay, so if we construct the tree, then we will spend, well, maybe an alpha n or n log n to construct this envelope, and then I'm going to spend another, well, but here n will be n divided by 4 maybe, another n alpha n to construct this one. But when I answer the query, okay, then the only thing I need to do here is do binary search on this thing. And then I know, well, I'm between here and here, check whether I'm above or below. So in log n time, I know where to go. So in total, I have log squared. But I will come back to this later.
Here in your picture, the left triangle, that's the left.
Left.
Yes. The right edge of this left triangle is not completely in the upper bound.
Yes. Yeah.
So when you project this, you will make this triangle completely, this edge completely the upper envelope of your map. So how do you handle this?
Yeah, so indeed when I project my triangles, so maybe in this case this would be this left triangle, then here I have another triangle where this one is behind here. So the upper envelope is going to be the upper envelope of, well, I have a collection of segments that intersect each other. But that's fine. I mean, we looked at upper envelopes of intersecting segments. And so what I want to compute is, I simply compute this. That's it.
If you're looking at the top, you cannot see that this part of this edge is below of the other.
So I'm...
When you look at these two triangles from the top.
From above.
From above.
Okay.
So
so from above, it maybe it looks... let's see. Maybe I have something... I don't know. Maybe something like this. This is from above. Now it could be that this triangle is this one, and this triangle is maybe this one. Okay, but when you now look from here, this one is, well, in front, a little bit in front of the other one.
My main problem is your first picture when you wanted to. Yes, this the left. So when you project this plane and you look from the above, those four so
pyramids,
you
or
will see them like a square that have a point in the middle. And
yes. So that could be that those look like this. You mean?
So in the middle of some of these triangles, you will not. There are not. Those that's green one triangle is behind these two. So when you project these like this, you can see that one. You see what I mean?
I don't. Does somebody else understand the question, or can maybe rephrase the question? Or okay, so maybe we can later. Okay, so now I want to compute this ordering on the triangles. Okay. So
all this is for a fixed query.
So this is all for a fixed point Q. Okay, so I have my point Q, and well, I say that, let's say this triangle is smaller than this triangle if I have an array first intersecting this one and then that one, and now I want to find an ordering which is consistent with this thing. Okay, so first question is it actually possible always? Well, no. Right, so here this one is before this one is before this one is before this one, and this one is before this one. So I have a cycle. Okay, similar to we did this depth ordering in 3 dimensions. You can have a cycle here, you can also have a cycle. So I cannot find such an ordering, or not always, but there's a very simple trick to avoid this problem. So if I split the terrain into 2 in this way, by, let's say, a vertical line through the point Q. So now I have 2 sets of triangles. Well, actually you get 4 gons if you want, you can triangulate them. So now I have 2 different things. So I'm going to compute an ordering for these guys, and I'm going to compute an ordering for these guys. Okay, so in other words, you could say I have a data structure for Q when my rays are going to the right, and I have a separate data structure when it's going to the left. Okay, so let's only look at this part and forget about this one. So now my point Q lies, let's say I have a set of triangles, and my point Q lies outside the convex hull of these triangles. So what I had before, this cannot happen anymore because this was in the middle of these triangles. And so my claim is that after doing this, there cannot be any cycles, and so I can find an ordering. So let's try to prove this. So I claim that when Q is outside the terrain in the projection, outside the convex hull, then I always have an ordering. And the way to prove it is, well, we want an ordering with respect to this comparison operator. And I'm going to prove that I always have a maximal element. In other words, there's always a triangle which is not in front of anything else. So a triangle that could be the last one in the order. Okay? So is it clear that if I can prove this, I know that I have an order? Right? Because, well, I have a maximal element. I can put that last in the order. I remove it, and by induction, I have a last one on the remaining one, and so on. So this is the only thing I have to prove. And that's actually a relatively simple way to argue this. So look at all these triangles. So here they're not allowed to intersect. They are allowed to touch, to share an edge. But it's slightly easier to think about it when they're disjoint. So I've drawn them disjoint. And now for each of these triangles, look at, well, I've called it here the bottom vertex. What I actually mean is, let's say that this point, it was outside the terrain, so let's say it's to the left of all the triangles. That I take a line here, half line, and I rotate, and I take the first vertex that I hit. So that is what I call the bottom vertex. And then the last one, well, that would be the top vertex. But I look at all these bottom vertices. Oops. So this is a bottom vertex, this is a bottom vertex, this one, this one, this one, and so on. And I'm going to look at look at all the bottom vertices such that if you take this ray, from this point on, you don't intersect anything else. Okay? So first, I say that there must be at least one such vertex. Why is this? The very first one, right? So if this is to the left of all the triangles, so this doesn't intersect anything. I rotate until I hit the first one. Then, well, this is the first time you encounter a triangle, so this definitely doesn't hit anything. So I know that there's at least one such vertex that can, well, let's say, see infinity. And now of all the ones that can see infinity, I take the topmost one. So of all the ones that can see infinity, I take the one that I hit last in this ordering. So that's this guy, right? This could also see infinity, this also, but this is the last one, because all of these cannot see infinity. Now I claim that this region must be empty. Why is it empty? Well, this doesn't hit anything. So if there's a triangle somewhere here, it must, I don't know, be completely inside or maybe here, but it doesn't cross here. So in particular, as soon as I hit something else, it will be a bottom vertex, which can also see infinity. And that contradicts that this was the last one that can see infinity. So this is empty, so it's a maximal element. Right? There's nothing here, so this is not in front of anything. So it's my maximal element, and I'm done.
The triangle in dark green is the solution of our problems. We were looking for a triangle that the ray hits. I'm making this poll. We were looking for the last elements that you cannot through infinity from there, and also find another one. But the result of this step will give us a real huge amount of triangles that in a chain, I say, that will give that the solution may be lays inside one of them.
No, so this is not part of the data structure for answering the ray shooting query. So this only tells me that an ordering which is consistent with this in front behind relation exists. So this green one has nothing to do with the first triangle that I hit or anything. It's just this green one is a maximal element with respect to this ordering. Okay? And so what I wanted to prove was that such a maximal element exists. Okay? Because such a maximal element exists, there must be an ordering, because you can apply it recursively. And now that I have my ordering, I can build this tree because I know how to order these things. Right? So what I do is, in the pre-processing, my point Q is fixed. I project everything. I split the terrain into two parts. Okay? I build something for this one and for this one. So let's forget about this one. That's just the same structure but then reversed. How do I construct something for this? Well, that's still pre-processing now. I sort the triangles according to this relation. I know I've just proven that this is acyclic, so I get an ordering. Now I build a tree on this ordering. For every node in the tree, well, I have all the triangles in the subtree, and I compute this. I compute the upper envelope, and I make a binary tree over it so that I can do binary search. This is my pre-processing. And now the query algorithm is, well, what we said before. You get to a certain node, initially the root. If my ray hits when you're at the leaf, okay, then you simply check the triangle and report it if necessary. Otherwise, okay, you check if this ray passes above all the triangles by doing binary search in this upper envelope, log n time, and then depending on the outcome, you go to the left subtree or the right subtree. Okay, so the query time, so how much is the query time? Log squared n, right? Because I had this tree, I have log n nodes on the path. For every node, I do a binary search on the upper envelope. So log n times log n is log squared. What's the amount of storage? Well, I have lots of these upper envelopes, and the amount of storage is basically the sum of the complexities of all these upper envelopes. And how much is that? Well, so one way, what we normally do is write a recurrence, right? At a node, I have an upper envelope, which has complexity n alpha n, and I have a recursively defined structure here and here, so 2 times S n over 2. Right, which solves to n alpha n log n. Okay? You can also say at every level of the tree, a triangle is present in only one of the envelopes. So if you sum up the sizes of all these envelopes, well, you get something like some Ni alpha Ni, and I know that some of these Ni's over one level is linear, and so this will be n alpha n, and I have log n levels, so that's a different way of doing it. Okay. Yeah. So actually this square in the query time is not needed. We were going to do log n searches. Each search is a binary search on some ordered list, and then, I don't know, for those of you who know fractional cascading, they will see that you can apply fractional cascading. Okay. Any questions about this part?
What's the time to construct the tree?
The time to construct a tree, so each of the upper envelopes. Okay, so the easy argument is to say, okay, each upper envelope, actually you can compute in n log n time. Okay, so that means that if you look at the pre-processing time, instead of n alpha n, I have n log n here. Then you get n log squared n. But actually, you can do it more efficiently, because if you build this tree bottom up, okay, then, well, by the time I get here, I know the upper envelope here, and I know the upper envelope here, and I can just merge these upper envelopes in linear time, and then the whole pre-processing would be n log n instead of n log squared n. Okay. Second application. Nothing about data structures, nothing fancy, just computing the number of views. So again, I have a terrain. Okay. And now take a vertical line. So this vertical line is now fixed. Okay. And I wonder if I move my viewpoint, let's say like this, over this line, then what I see in the terrain is going to change. Okay, so for instance, maybe from here I see this picture, but when I go higher, what happens? Well, I guess you can imagine that essentially these peaks go down, right, until at some point, maybe when I'm here, you actually, when you look over these peaks, you see here. Right? So I guess you can imagine that sort of this, this view changes. So now I wonder, how often do I get a change in the view? And what do I mean by change in the view? Well, the view is changing continuously, but only at certain times the view changes, let's say, in a combinatorial sense. Right? So first it changes just a little bit, but the structure of the view is the same. But when you go up, at some point maybe this peak goes, it used to be above this edge and now it goes below. Okay, so the question is, how often can this happen? And, well, if you look at this example, how many changes in the view would there be in this example? N squared, right? Because probably for each of these peaks, when my viewpoint goes up, this peak essentially goes down and it goes through all these edges here. So in this example, I have n squared changes in my view. if you think about it, you can even have n squared alpha n changes in the view. So it's basically the same example, except this part in the front, instead of having separate peaks, what you can also have is that in the front you see, okay, this is a triangle, but there's something else maybe here in front and here and here. So the front, here the front was simply peaks, but in general the front is going to give you some kind of upper envelope. And now the back, it could be that, well, maybe I should make it red. Oops. That the back looks like this. Then this whole upper envelope is going to pass all these edges. And the upper envelope can have complexity n alpha n. So then you would get n squared alpha n. So what I want to prove now is that it cannot be much more than this. Okay, so to prove this, let's see, when does the view change? Okay, so one thing is what you see here. When my point Q goes up, then at some point here this peak goes below this edge. Okay, when does that happen? Well, exactly when the ray from Q through this vertex, if I continue, it hits an edge. Okay? Well, for every pair of vertex edge, this happens only once. Okay, so of this type of events, when I move up, I have only n squared. Okay, so that's easy. But there's also other events, other things where the view changes. And actually we already saw that here. For instance, let's, oops, maybe this one, this vertex, maybe also passes through all these things here. But this is not a vertex of the terrain, but it's the intersection of two edges. So here I have maybe a better picture. Okay, so let's say that from a point here, what I see is this picture. So I've here the first edge, then the second edge, which is behind this triangle maybe, and then I have a third edge, which is behind these other two. So these edges, 1, 2, 3. And now when I move my viewpoint, also these edges move. And it could be that this edge, maybe before you couldn't see it. Right? It's the last one. If I'm a little bit too far down, I cannot see this edge because it's hidden by these two triangles. But when I move up, then this one suddenly becomes visible. Okay, so this is also something that can happen. And actually, for each 3 edges, this can happen, well, actually, a constant number of times. So now it's a little bit tricky to see how often this actually can happen. You have to look at some of the equation, but this happens actually only twice. It can happen twice. Right? So imagine that if I have a line that goes through this edge, this one, and this one, then this line can still move a little bit while still touching all the 3 edges. Because a line has, you could say, 4 degrees of freedom. I don't know, pick one point that's 3 degrees of freedom and a direction. So And I've only 3 edges, so I still have 1 degree of freedom left. But actually, so that means that there's lots and lots of lines that pass through these 3 edges, but the ones that also go through this vertical line, then, well, it seems that there can be 2. But I'm looking at a triple of edges, so I can have n to the power 3 different triples. So potentially, this happens n to the power 3 different times. Okay? Our lower bound was n squared, or maybe n squared alpha n. So now the question is, can we come up with an example where this really happens n to the power 3 times? And the answer is no. And we're going to prove that using some bounds on envelopes. Okay. So what I'm going to do is the following. So such an event had, well, I have a line here that passes first through E1, then through E2, and then it hits E3. Okay? So I'm going to fix this edge. And now I claim that the number of pairs E1, E2, where something like this happens, well, the naive bound would be to say, well, I have n squared pairs, so it can happen n squared times for this fixed edge, but I'm going to prove that it's only linear, or actually lambda 4. Okay, and of course, if it's lambda 4 for a fixed edge E3, well, I can choose E3 in n different ways, so I get n times lambda 4. Okay, so n squared and not cubic. Okay, so here this is where the envelopes come in. Okay, so I've fixed this edge, which is this edge E3. Okay, so now this is a top view. So here I have E3. I have this line from my point Q, and maybe, it touches E1 and E2, or maybe this could be E1 and that E2. Right? So I want to see how many of these pairs can give me such an event. Okay, so I'm going to define a number of functions in the following way. So I'm going to parameterize this point here on this last edge by a parameter lambda. So this is maybe P0, and then here I have P1. And in between, so lambda goes from 0 to 1. And these are my points. Okay? So now look at a cross-section. So I look at a point P lambda, and look at the vertical plane that goes through this point and my point Q. Okay, so that vertical plane will contain this line. So this is this vertical plane. Okay? So here I have my point P lambda in this vertical plane. And now each of these edges here, they will intersect this plane in a point. Okay, so those are my points. So you have to imagine that there's this terrain here, and I have edges passing through these points. Okay? And now the function I'm going to define, so look at this edge E. So I have an edge E here. Take my lambda. Look at the line and this point. Okay? Continue until you hit your line L here. And this, let's say this distance, maybe this is z equals 0. This distance is going to be the function value for this edge. Okay? So this height depends on lambda. Okay? If I change lambda, if I change this point, then this plane here is going to rotate. So the heights of these things are going to change a little bit. So this line is going to change a little bit. So I get different values here. Right, so this is a function of lambda, and I can define such a function for each of my edges E. Okay, so now think about what happens when I have a situation like this. So I first hit E1, then E2, then my fixed edge E3. Okay, and let's say this happens, well, for this point P lambda up there. Okay, so how does it look in this picture? Well, apparently I have a line that goes through, well, this should be maybe E2, right, because it touches here. It also goes through, so there should be an E1 here. And these two should be the highest two, right, because as soon, if I would have, let's say this E2 is here, but E1 is up there, well, then my this thing hides what is behind it from the view. So if I have an event like that, then I must have, let's say, E1 being here, E2 being here, and these are the highest two. So in other words, if I look at my functions, then for this particular value of lambda, I have these two functions which have the highest value, and all the other ones should be lower. Okay, so a situation like this corresponds to a vertex, a breakpoint on the upper envelope of these functions. Well, my upper envelope has complexity, well, depending on how often they can intersect. But if you do the computations, you will see that they intersect at most twice. So this upper envelope has complexity lambda 4 of n. Okay. So do you all see why these events must be this? Right, so maybe to repeat, I must have an event is, well, I have a line where I can actually see all of this up to E3. Okay, so in other words, if you see that, if I take, if I now, let's say, take this line, so I see E1, E2, E3, that means that if I'm looking further up, there's nothing there. Okay? So what does it mean here? It means that if you look at all these points, you go through, let's say, E1, E2, E3, and if I move this line up, there are no other vertices. Okay? That means that, well, if these are both here, then for E1 and for E2 I get the same function value, and all the other ones are below, so I get a lower function value. So at this lambda, these two have the same function value, the other ones have a lower function value. Now if I vary lambda, then you can bound the number of events that you get, okay, by this upper envelope, which is m alpha n. Okay, so there are lambda 4 pairs that have a type 3, type 2, I guess. Type 2 event, so an event with 3 edges involved. And since I can fix my edge E3 in n different ways, I get the total bound of n times lambda 4. Okay, so it's slightly more than the lower bound, which was n squared alpha n, but the difference is extremely small. Okay, any questions about this part? So I have 3 more applications for you. They're all about the same thing. So actually, and they are actually very easy. So what I'm going to do is simply state these questions and give you a little bit of time to think about them. So they're all about points moving. Okay, so I have a set of points. They're moving, points in the plane. Let's say the motions are, I don't know, either straight line motions or maybe they move along a polynomial of degree s or something like this. So simple motions. And now I want to know something like, okay, how often does, so this is now the nearest neighbor, but when these things start to move, the nearest neighbor can change. Or sorry, the closest pair can change. Right, so how often can, I wanted to do closest pair. How often can the closest pair change? Or how often does the Delaunay triangulation change? Or how often does the convex hull change? Okay. So let's first do this. So I will, to get a little bit of insight or to get used to the problem, let me say what the obvious bound is. Okay, so I have n moving points. Okay, so when the closest pair changes, then apparently I have 2 distances that become the same. Okay, I have some distance here and some. So one way of analyzing it would be to say, okay, how many distances do I have? Well, between any 2 points. So if n squared distances, well, I can, so how many pairs of distances do I have n to the power 4? Well, probably if these points move along polynomials of bounded degree, then the number of times these distances become the same is also is some kind of constant. Right? You get some polynomial probably of degree 2s that should be 0 when these distances become the same or something like this. So the naive bound is that you get O of n to the 4 changes to the closest pair. And because this distance, maybe this used to be the closest pair, and now this becomes the closest pair, so there are 4 points involved. You can choose them in n to the power 4 different ways.
For each 2 points, you can have a formula that determines the distance of the 2 points. It's okay. In terms that the formula of movement of each point. And when you put all these functions in a plane, the lower one of these functions will be the nearest neighbor. So the complexity of lower one was n alpha, I think. So
yeah, so very good. So what I could simply do, instead of saying, okay, I have my n squared distances and I have to compare each of them, what I do is exactly what you're saying. I now define for every pair, let's say pi, pj, I define a function, let's say fij, which is a function of time, which is the distance between pi at time t and pj at time t. Okay, so let me plot all those distances. So here I have my function, I don't know, so this is t. This is, f1, 2, Here I get f1, 3, and so on. So I have n squared of these functions, and the closest pair, well, is the lower envelope of these functions. I have n squared functions, so the lower envelope has complexity n squared alpha n squared, which is the same as n squared alpha. Yep, very good. So that was the first one. Okay. Second one. How often does the Delaunay triangulation change? Okay, so how does it change? Well, what happens is that, let's say, I have a set of points. I have my Delaunay triangulation. Maybe like this. Okay. As you know, hopefully, the Delaunay triangulation has the property that if I take the disk through the vertices of a triangle, that this disk is empty. Right, so what happens is that, for instance, let me change the picture a little bit. Oops, wrong color. Okay, if this point here is going to move inside this disk, then this is no longer a valid triangle. So what happens at that point? You flip the diagonal. Right? Instead of, if this point moves inside, so maybe all my 4 points were exactly at a circle. So before it was, when it's here, it looks like this. But when it moves inside, you flip the diagonal. Okay, and these are essentially all the changes. Well, you have to look at the convex hull a little bit separately, but okay, so what's the naive bound on the number of changes in the Delaunay triangulation? N to the power 4, right? Because apparently you have a change when 4 points, so when 1 point moves into the circle of 3 other points. So when you have 4 points that are on the circle, and if the points move, let's say, along polynomials of bounded degree, then any 4 points can become collinear only a constant number of times. Okay, so n to the power 4. Okay, exercise. Use envelopes to improve this to roughly n to the power 3. Okay, so this is a little bit more difficult than the previous one. Okay, so you can already maybe get a little bit of an idea how to do it because of the time bound. So I claim that the bound is going to be, instead of n to the 4, it's going to be roughly n cubed. Or actually, it's going to be n squared times lambda, I don't know, something, where this depends on the degree of the functions. So if you look at the bound, then here you see this upper envelope, lower envelope bound. Okay, so apparently we get n squared times the lower envelope bound. So that would suggest to say, somehow take a pair of points, I have n squared pairs, and for each pair try to argue that you only have lambda changes that involve this pair instead of lambda squared. Instead of n squared. So in my picture here, I have 4 points. 1, 2, 3, 4. Okay. Let's say I fix these 2 points. Okay, so this is some fixed pi, pj. So each of points will give only, well, a constant number of these events, but I could have n squared of these other pairs. So now I want to argue that if I fix these things, these 2 points, that, well, the number of changes is only near linear instead of quadratic. So can you come up with some kind of functions such that if we want to have an envelope, let's say a lower envelope, then we want to define the functions in such a way that, well, each of my points defines a function, that these two have the smallest value for that function. And they have the same value. Right? And if this is the case, then, well, I get some envelope. So any idea how to define these functions?
For example, in coordinate diagram, when 2 points, when you change the nearest point of and a point, so the property of coordinate diagram and the nearest point. So when the nearest point of and points change, the coordinate diagram will change. So if you map distance of point 1 with each point, when the nearest point of point 1 change, the coordinate diagram will change. So it's kind of the lower bound of the mapping all distance between point 1 and other points.
Yeah, so I don't quite understand what you want to do. So here I want to define, so I fixed I and j. Okay, so I want to define now for each point k, I want to define a function of time. And actually this function depends also on these fixed point I and j, but they're fixed. And somehow, so one way of thinking about it is to say, if I have for each point, okay, for each other point, I have one disk which goes through these 2 points and this other point. Okay, so for instance, for this point here, I have a disk that looks like this. Okay? Or simply the size of the disk will work. So one way to think about it is, okay, I have this I take my edge. Now imagine I have this circle, and let's say all the other points are here for simplicity. I have this circle that I'm now pushing through this edge. So it's getting bigger and bigger on this side. Oops, and so on. And then since here, when this is an empty foregone, then these are the first 2 points you hit. So for each point, you simply take this circle, and then, well, let's say for these 2 points, it's simply the radius of this circle. So all these distances are actually the same. Okay, then in my Delaunay triangulation, I'm going to have a triangle. Then this one should have the lowest value of this function. Right, because this is the first one you hit, then it's still empty. After that, it's no longer empty. Okay. And then I get such an event exactly when 2 of these distances become the same. And actually, they both have to be minimal. So you get, again, a vertex on the lower envelope. Okay, so that means that if I fix this one, I can do that in n squared ways. I have some lower envelope, and that's it.
You're talking about the expansion of a disk, expansion of an empty disk of points, in for each triangle inside the preliminary triangulation. But there's no specific points defining the center of the disk, and from there the expansion starts. I think we were talking about the first point when the expansion hits. That's the point that we are talking about. But in which direction?
Yeah, but that's okay.
Along this bisector of that point, along with.
So indeed, this is. Yeah. So that must be along the bisector of this one, because the disk must go through this point and this point. So its center must lie on the bisector. Right? So essentially, you can say, well, I take the center goes from here upwards, and then these disks start to look like this. So you're pushing it through, so there's only one way of doing it. And then you can also say, well, here I looked at the radius. You can also say simply the time, well, time is a little bit confusing now, but the moment when you hit the first disk. So the position of this center could be.
On the other hand, we have three edges of a triangle for each empty circle, and we have 3 bisectors. So choosing one of them that the expansion starts from there, it seems to be something at random.
No, so now remember that I fixed pi and pj. Right? And this does mean that every event I will count it 3 times, or 4 times maybe for each of the edges. But for fixed pi, pj, that's, yeah. Okay. So actually this was one of the main open problems in computational geometry for a long time. So this proves a bound which is roughly cubic, right? N to the power 3 or a little bit more. The best lower bound was n squared. So if you look at points moving along a line or simple curves, nobody was able to give an example where it changes more than n squared times, but nobody was able to prove that it's always smaller than n cubed. So recently, and last year, there was, well, actually 2 follow-up papers by the same person where he proved that the right bound is actually n squared, or n to the 2 plus epsilon, actually. So there used to be a nice open problem here, but you can maybe try to, instead of n to the 2 plus epsilon, try to prove n squared alpha n or something. But I must warn you that n to the 2 plus epsilon paper is 90 pages. So it's not very easy. Or maybe you have a very clever idea that in 2 pages you can do it. Who knows? Okay, let me skip the last one. But just in general, if you have moving objects, right, and essentially the number of views, you could also think about this as moving objects, because when the viewpoint move, these edges start to move in the view. So when you have moving objects and you want to analyze how many changes there are in certain structures, then you almost always end up by looking at envelopes. Okay, so well, this is what you've seen. So I hope you learned something, and I hope you actually liked it. Even more important, perhaps. And so that's it for the course. But maybe also, well, like Joachim, I would like to thank, well, of course, Professor Mohades and all the people who have helped in organizing and so on. So I was in Iran once before for another winter school, and I think it's amazing how friendly everybody always is. It's, well, everybody asking you all the time whether they can help you or something. So I think it's very nice. And I think the other thing, what Joachim says, it's also really nice to see so many students who are interested in the topic and want to work on things. So sometimes I wish we had so many enthusiastic students in the Netherlands. But yeah, so it was a real pleasure. That's a good advice. So well, thanks again, and I hope you enjoyed the winter school. Thanks.